Hello everyone, welcome to our lecture video. In this lecture video, we are going to design a rectangular beam for a 4 meter effective span which is subjected to a dead load of 15 kilonewton per meter and a live load of 12 kilonewton per meter, and we have to use M25 mix and Fe500 grid steel. So before beginning this question, we are going to be use two different code books for the problem. We are going to be using SP16, and next we are going to be using the IS 456 2000. So you need to need both of these codes in order to solve this problem. You can either have the hard copy or the soft copy. So let's begin this question. So this is our problem 2 under our design of beam. I have already solved many more problems under the RCC chapter similar to this, which link you can find in the description box below. So let's begin this question. So firstly, what we have is we have a 4 meter effective span of the beam. So we have 4 meter effective span of the beam, and it is subjected to a dead load of 15 kilonewton per meter. It is subjected to a dead load. So let me just draw the dead load this way. The dead load is 15 kilonewton per meter, and it is subjected to a live load of 12 kilonewton per meter. So we need to design the beam using our M25 mix and Fe500 grid steel. So first and foremost, we have given the length, so we need to find our effective depth, which is our D. So let's say this is our beam design, then this is going to be my D, and this D is up to the center of this reinforcement bars, and my overall this is going to be my D, is going to be overall depth, and this is going to be my breadth of the beam. So in order to design my beam, I need to find my B, and then I need to find my effective depth, as well as I need to find my number and the diameter of reinforcements which we are going to use. So what we are going to do, assume first of all is assume we are going to assume the length, the ratio of L by D from the range of 10 up to 16. So right now we are going to assume the ratio as 10. So we are going to assume L by D equals to 10. Then my D is going to be L by 10. So I have my L as 4 meter. So 4 divided by 10, this is going to be equal to 0.4 meter, or which is equal to 400 millimeter. So I found my effective depth D. Next, what we're going to do is I'm going to assume my effective cover. So effective cover is the distance from the center of this reinforcement over here. This distance is going to be my effective cover. So it says effective cover. So normally for beam we are going to assume minimum effective cover of 25 mm. So in this case we are going to assume the effective cover of, so let's say assume effective cover, assume effective cover D dash as 50 mm. You need to for any beam you need to assume this minimum of 25 mm. So right now you can assume any value greater than 25 mm, which can be 30, 35, 40 and so on. Right now I'm assuming 50 mm. So my overall depth, therefore overall depth D equals to D plus D dash. So overall depth is going to be D plus effective cover. So my D is 400 plus 50, so 450 mm. So next, as I mentioned before, I am going to need the B. So what we have next rule is we are going to assume the B by D somewhere in the range of 1.5 to 3.0. So on calculating this, so we need to find the value of B. So I have the value of D as 400. So you can choose any value between 1.5 to 1.5 to 1.3. On doing this, I'm going to get my value of B as 250 mm. So you can directly assume the breadth as 250 mm. The breadth is always going to be less than the depth, so you can put on a certain assumption as somewhere value less than 450, which can be like 200, 250, 300, anywhere. But if you need if you say I cannot assume a certain value, or for easiness, what you can do is the ratio of B by D needs to be in the ratio of 1.5 to 3. So if you do this, we have the value of D. You can easily get the value of B. So moving on, what we have is we need to find out the self weight of the beam, or we need to find out the total load. So why do we need to find out total load? In order to find the moment, we need to find the total load. So next, what we're going to do is we're going to find the total load after this calculation. So from our previous calculations, we found the value of D as 250 mm, while we found the value of our effective depth D as 400 mm. So moving on, what we're going to do is we need to find out our total load acting on our beam. So what we need to do is we have our so first what we're going to do is I'm going to calculate my self weight of the beam. So why I am self weight of beam? So self weight of beam is W equals to gamma V. So gamma into V, we have W equals to gamma V. So right now V is area, cross sectional area into A into 1. So right now we are taking the unit height. So we are going to have A. So gamma into cross gamma C is the unit weight of concrete, which is 25 into A. Area is equal to our breadth into depth. So what is our breadth? Our breadth is 0.25 into our depth is overall depth. So we're going to take our overall depth was 450 mm. So our overall depth is 0.45. So on multiplying this, we are going to get our self weight of the beam as 2.81 kilonewton per meter. 2.81 kilonewton per meter. So previously we had our live load of 12 kilonewton meter, dead load of 15 kilonewton per meter, and our self weight of the beam is 2.8 kilonewton per hour meter. Therefore our total load is going to be our total load is going to be 2.81 plus 12 plus 15. So on summation of this, we are going to get the value of 29.81 kilonewton per meter. So this is our beam. So our normal beam. So in our normal beam, we have our maximum bending moment. So what we have learned is, for our beam, the maximum bending moment, this maximum bending moment is equal to WL square by 8, where our W is our load. So we are going to get our maximum bending moment, which I am denoting as A. Then maximum bending moment M equals to WL square by 8. So in the place of W, I am going to place 29.81. Our value of L is 4. 4 square is 16 divided by 8. So on multiplying this, we are going to get our value as the value of maximum bending moment is going to be 59.62 kilonewton meter. So we got our value of maximum bending moment as well. So as I have already explained before in my previous videos as well, we are designing the beam using our limit state method, and under our limit state method, what we do is we increase our load by certain factor while we decrease our resistance. So what we are going to do is, this is our unfactored bending moment. The bending moment which we have calculated is unfactored bending moment. So following the assumptions of limit state method, we are simply going to find out the factored bending moment. So factored bending moment. So in order to find out the factored bending moment, so let me write factored bending moment as mu. So in order to find out the factored bending moment, I need to increase my bending moment by 1.5. So I'm going to get my factored bending moment mu as 89.43 kilonewton meter. 89.43 kilonewton meter. So after this, what we're going to do next is, we need to find out our effective depth of the beam, and let me explain why we need to calculate our effective depth. So now the value of factored bending moment, which is calculated mu, which is our factored bending moment, was 89.43 kilonewton meter. 89.43 kilonewton meter. So now what we're going to do is, we are going to check for effective depth. So why we are checking for effective depth is because we need to find whether our beam is under reinforced or over reinforced, or it is in balanced section. If it is over reinforced, we need to design our beam one more time, because we never design our beam for over reinforced section. While if our beam is under reinforced or over reinforced section, we have specific two different formulas to calculate our area of steel. So first we need to check out whether our beam is under reinforced or over reinforced. So right now we have already found our value of D 400 D as 400 mm. So using this value, we are going to find out whether our beam is under reinforced or over reinforced. So what we are going to do is, we are going to use mu limiting equals to mu. So now we are going to follow our code book. So now we are going to follow our SP16 code book, and we are going to turn on to page number 10. So if you have PDF, you can scroll to page 10, or if you have hard copy, you can scroll to page 10 as well. So what we have over here in page 10 is limiting moment. Right over here, limiting moment of resistance and reinforcement index for singly reinforced rectangular section. We have mu by limiting equals to, we have right now we are using Fe500 grid steel. So for our Fe500 it is 0.133. So mu limiting equals to, so right now I need the value of mu limiting. So mu limiting is going to be 0.133 into FCK BD square. FCK BD square is in a denominator, so we need to multiply it. So hopefully you have seen it is in page number 10 of SP16. So mu limiting is equal to 0.133 into FCK BD square. We have calculated our, so right now we are designing our beam for balanced section. So this means mu limiting equals to mu means balanced section, balanced section. So we're right now designing our beam for balanced section. So we have mu as 89.43 kilonewton per meter. So if I multiply it into 10 to the power 6, it goes into Newton millimeter. So we have 0.13. FCK is my characteristic compressive strength, which is 25 Newton per meter square, 25 Newton per mm square. So I'm going to place 25. I'm calculated my B as 250 mm into D. This D is actually my delimiting. So I have delimiting whole square equals to 89.43 into 10 to the power 6. On solving this, I'm going to get my delimiting as 328 mm. So I have already, so the limiting depth which I need for my rectangular beam is 328 mm. So but right now we are designing our beam for 400 mm. So we have our D is greater, our this D is going to be greater than 328 mm. Our D is greater than delimiting, so this means our beam is under reinforced section. This is my under reinforced. If D equals to delimiting, it is balanced. But if if delimiting is greater than D, it is going to be over reinforced. We don't design such kind of beam. We need to re-evaluate our design. So let me explain why if D is greater than delimiting, it is under reinforced. So here what we found was we found out our D is greater than delimiting. So we said under such condition our beam is under reinforced. So many people just mock up this but don't know the reason behind this, how it is under reinforced. So let me give you an example. So let's say this is our shortened beam. So let's see if we are increasing the depth of the beam. Let's say we are increasing the depth. Let's say if we have kept a huge depth of the beam, in such condition we are going to use more concrete or more cement in a simple sense. In that case, we are going to be using less reinforcement. The reinforcement are going to we are going to keep less reinforcement, or the reinforcement are going to take less stress. So in such condition, the reinforcements are going to be less, so under reinforcement. So let's say in other condition, if I limit the depth and if I keep small depth, so in this condition, in order to take the load, we need to give more number of reinforcement. If we use less D, then required of if I keep D less than delimiting, in that case I need to use more number of reinforcements so that my beam structure does not fail. So the reinforcement is taking the more amount of load, or if the or in simple terms, the reinforcement is high in number, so it becomes over reinforced. So hopefully you have understood the concept of why if D is greater than delimiting, it is under reinforced, and if D is less than delimiting, it is over reinforced. So moving on to our next portion, we are going to find out our area of steel. So as I explained before, we have different formulas for our under reinforced, over reinforced, and balanced section in order to calculate our area of steel. So for that reason, we had to check whether our beam is under reinforced or in balanced section. If we had found out our beam was over reinforced, we'll have to design one more time. So next, what we're going to use the formula is we have mu equals to. So again we're going to follow our code, but this time we're going to follow our IS 456-2000. So if we move on to our last page, in Annex G, what you find is we have our formula of if the value of x by D is less than limiting value, which means it is in our under reinforced section, we have our value of mu as 0.87 f by ast d1 minus. We're going to use this formula of B. While if we had limiting section, if we had for our balance section, we will be using the formula mentioned in C. So right now we're going to use this formula for our under reinforced condition. We have mu equals to 0.87 Fy ast D minus 0.87 Fy ast D minus Fy ast divided by FCK B. So this is in our Annex G of IS 456-2000. So as mentioned before, we found out the value of Fe, which is our factored bending moment, as 89.43 into 10 to the power 6 equals to 0.87 into Fy. Fy is my tensile strength of my steel, which is 500 kilonewton per millimeter square. Next, I'm going to put AST as AST. I found my value of D as 400 minus Fy. The value of Fy is again 500 into AST divided by FCK is 25 into B is 250. So on solving this, I'm going to get my value of AST as 581 millimeter square. So if we get two value of AST, we should always use the minimum. We should use the minimum value. Next, what I need to do is I need to check whether this area of steel which I obtained is up to the code or not. So for that, I need to find out the minimum area of steel. So in order to, so let me just write out here, check for minimum area of steel. So my formula for minimum area of steel is A0 equals to, A0 is my minimum area of steel, 0.85 BD divided by Fy. You can find this formula in your code as well, in the same code of IS 452,000. If we move in the page number 47, you can find this formula. A0 by it is written AS by BD equals to 0.85 divided by Fy, where AS is the minimum area of steel required. So we are going to place 0.85 into B. My B value is 250, my D value is 400 divided by my Fy value is 500. So on solving this, I'm going to get my A0 value as I'm going to get my A0 value as 170 millimeter square. So the minimum area of my steel required for this dimension of the beam is 170 millimeter square, but I have obtained my my area of steel as 581. So it is 581 millimeter square is greater than 170 millimeter square. Therefore my design is correct. So finally, what I need to do is I need to find out the number and diameter of bars. So the total area of steel reinforcement which I am going to use is 581, but I need to find the number and diameter of the bars to be used. So next we are going to follow that. So now let me put on the calculation which I have done. So let me draw the beam which we have created up to now. So up to now we have found out the depth of the beam. So till now we have found out our depth of the beam, we have found out our effective depth as well. So we have found our depth of beam breadth as 250 mm, while our effective depth is 400 mm. So now next we need to find the amount of reinforcement to be used. So right now the area of steel which we are going to use is 581 millimeter square. So now number and diameter of bars. So the process which we are going to do is complete hit and trial. It's complete hit and trial. So let me show you how we can do it in a more easier way. So let me write out the different number of bars which we have, different diameter. It's the diameter of bars and it is area. So in our market, the diameter of bar which we commonly find are 8, 10, 12, 16 and 20. It goes up to 25 and 32 as well. So the area of 8 mm bar is 50, 10 is 30, 10 is 78.5 and 12 is 113,201, for 20 is 314. So you can simply find this area by using the formula pi d square by 4, where d is 8. So next what I need to do is I need to design the total area of steel I'm going to need is 581. So as you can see, we need to design our beam in such a way that we cannot just put a single bar. So right now I have 400. So for 25 it is 491. So as you can see, I cannot use my bar of 20 mm or 25 mm because it is going to be quite large. I need to be using only a single reinforcement. So the basic two rules which I need to follow is the number of bars which I use must be symmetrical. So I can be using either three bars like this way, 3 bars. These are going to be of larger diameters, or I can use 5 bars. I should not be using a single bar or 2 bar. I should be using symmetrical as much as possible. So right now I have 581. So what I can do is I can use 2 bars of 16 mm, 2 bars of 16 mm, and manage by using a certain number of 12 mm bars as well. Or what I can simply do is I can use 3 bars of you can directly use 3 bars of 16 mm. So I have 201 into 3 is going to be equal to 603. So right now my area required is 581, which is quite close. 603 is quite close to 581. So this design is acceptable. So right now what I'm going to do is I'm going to provide 3 diameter 16 bars. So my area of steel provided is going to be area of steel. This is my area of steel required. So the area of steel I have provided is going to be 3 into 201, which is going to be 603 millimeter square, which is quite greater than which is almost in the near to 581. So this is acceptable. So what I'm going to do for my design is I'm going to use 3 diameter of 16 bars. So we can use so we cannot use 3 diameter of 20, because if I use 314 into 2, 314 into 2 is going to be 628, which is quite higher than 581. So our design must be as near as possible as to 581. You might use few 12 mm bars and 160 mm bar. You can manage it by heat and trial. It's completely heat and trial, but your bar must be symmetrical as much as possible. So as you can see, I have made my bar symmetrical in both sides. First requirement is fulfilled. Second requirement is I need to be the area of steel I have provided must be near to the area of steel required, 581. So I can design my bars in the range of 550 up to 650, let's say. So the area of steel provided must be in the range of 550 to 650. So fully you have understood how the design of rectangular bar for certain condition is done. If you like my video, do subscribe the channel, like the video and share with your friends. It will inspire me to upload more videos. Thank you.